Hello, I'm Sanaj Kumar, a PhD candidate from New Mexico State University, doing research and development for online. And I would like to share my work that is a word embedding topic model for robust inference of topics and visualization. Now, topic modeling can be described as a technique to draw out the hidden semantic themes, which are known as topics from the text corpus. So you can think of text corpus like talking about like a variety of things. So this variety of things can set to be a topic, and then as these topics are hidden, so we don't actually know like what exactly they're talking about. So what we do is in topic modeling, we try to denote these topics by a list of words, which can also be said as a distribution of words. And then this like list of words are very similar to each other in the sense that they have like an underlying theme behind it. So for example, we have like as topic one is talking about wireless phone mobile service communication company. So you can say like this topic is about phones, or this topic is about like a phone company or something. So this is how like topic modeling works. And then in the same research direction of topic modeling, we have a niche which is known as semantic visualization. So semantic visualization is like, I mean, we do topic modeling along with visualization. So we don't only like find out the hidden topics that are there. We try to like visualize the different like topic coordinates and the documents in a 2D or a 3D visual space. So this is like a upgradation over like topic modeling. So this technique was first introduced by PLSV, which is a short form of probabilistic gradient semantic visualization. And this method, like it works very well with long text, but it lacks behind in terms of performance in case of short text. Now, you would ask like, what is short text? So short text is nothing but documents that are short in length. So we have documents ranging from like 11 words to 15 words or 11 words to 20 words. So these like words, like these documents are really short. So what happens like in topic modeling, it is like based on word co-occurrences. So let's say like how often the word, let's say word A appears alongside word B, or how often like word C appears alongside word D, etc. So that's sort of like this is sort of the way like topic modeling does this thing to like extract out the hidden semantics. Now, what happens in short text is like these word co-occurrences are very sparse. So like the document length is not very long, it's from 11 to 15. So like we cannot build like a huge network of word co-occurrences. So in topic models, like they suffer a lot in terms of performance. Uh, so we already have some work done towards the direction. So we have Gaussian SV, which does topic modeling for short text as well as semantic visualization. But the only problem with Gaussian SV is like it takes a long time to just give out the results. So for large data sets, it just takes like astronomical amount of time to give out the results. So this was the motivation for our work. So our work was to like do semantic visualization for short text, and then topic modeling and semantic visualization for short text. And then also our method should like scale well. It should run fast. It should scale well with large data sets. So that was kind of the motivation. So how did we do that? So this is like kind of the way that we try to like navigate through it. So since we're doing visualization, we have a visualization space, as you can see. So we have the document coordinates, and document coordinates are all there in the 2D visualization space. And then we have an embedding space. So for the embedding space, since we don't have the word co-occurrences as the documents are very short, we leverage this information of like one word being like associated with another word using word embeddings. So as you can see, like we have the word embeddings on the left. And what we did is like we tried to embed the topic in the same space as the word embeddings. So as you can see, like topic 23 and topic 2, they are like very close to these words. So what we can say is like this topic is represented by like these words, which is look closer to. So in that sense, we can just draw out the word distribution for the topics, even for short text. So the visualization space, as you can see on the right, that's your topic distribution theta. The theta is like, I mean, if I go a bit technical, so the theta is just like a softmax between the document coordinates and the topic coordinates. And we have another softmax for the word embedding and the topic embedding. So that's kind of your word distribution on the left and the topic distribution on the right. Now, this is the generative process for WTM. So for each topic, we just like draw out the not raw. I mean, like we try to tie the topic coordinates and the topic embeddings together using a neural network. So we compute the topic embedding using that neural network, and then we try to like formulate the word distribution as you see in the previous slide, using the information from word embeddings and using this topic embedding. Now, after that, for each of the documents, we just draw a document coordinate from a normal distribution. And after that, for each word in the document, we just draw out a topic assignment from the topic distribution. And then finally, we just like draw out the word from the word distribution. So this is kind of the generative process for WTM. Now, for the inference part, so we use the fast AVV approach. Fast in the sense that it runs on GPU. So that's like the main thing why our model is like so fast. So the fast AVV approach has an encoder on the left-hand side and a decoder on the right-hand side. So what we do is from the left, we give in the data, and this data is encoded to a latent space. This like latent space consists of your topic coordinates, word, the document coordinates, the word distribution, and the topic distribution. And then like using this latent space, we try to like regenerate back the data. So the better we try to estimate these latent parameters, the better we are able to like regenerate the data. So that's kind of the logic behind AVV. Now, this is the general form for the objective function of AVV. And as you can see, like this is the form for our like WTM's objective function. So that was the inference part. We compare our model with 6 different baselines. So we have PLS3, Gaussian S3, probability, ETM, PTM, GPU, DMM. Of course, all the models do topic modeling. But for short text, we only have WTM, Gaussian S3, ETM, PTM, and GPU, DMM. These only can do short text topic modeling. For visualization, we have WTM, PLS3, and Gaussian S3. Now, these are joint models. So these can do like topic modeling and visualization at the same time. But for the other methods, probability, ETM, PTM, GPU, DMM, we have to apply t-SNE to get out the just visualize these the documents in like a 2D or a 3D space. So that was like this method is known like as a pipeline approach. Now, in terms of scalability, as you can see, like WTM and Gaussian SV are very close to each other. They like do topic modeling and for short text and also visualization. But Gaussian SV does not scale very well. So this is where like a WTM comes in. So WTM like scales very well with large data sets. Now, coming to evaluation metrics, we used like 3 evaluation metrics, which is KNN score, running time, and the NPMI score. So for KNN score, that just measures like the visualization quality, like how these clusters, like how together they are. And then for a given document, how closer it is to a document of the same class. So we try like different values of K, that is the number of neighbors, for getting out the KNN score. Now, we also like try to calculate the running time. We average the running time across like different number of independent runs. So that's the running time. And then we calculated the NPMI score. The NPMI score, like it just measures the topic coherence. So topic coherence can be thought of as a metric to just define how well a topic can be like interpreted by a human, how well it is like understood by a human, the topics that you have. So that's the NPMI score. These were the results that we got for the KNN for the visualization. As you can see, like WTM does very well for these things. So we vary the number of neighbors, and then we fix the number of topics for one scenario, and then for the other scenario, we fix the number of topics and we varied the number of neighbors. So that's kind of the way we did to like get up the KNN score. And then for the runtime performance and NPMI, we just like took the running time performance across different ones, and then we take the average of that. So as you can see, like Gaussian SV is taking like 150, 500, and then 1000 minutes for like running of the same data sets, while the other methods are just taking like 2-3 minutes. So that's like, yeah, that's super big. So it's not practical to like run Gaussian SV on like much larger data sets. So and that's the NPMI score, which you can see. And these are some of the visualization examples for all the like the top four models that produce the highest KNN score. So as you can see, like WTM did very well. Like it's like the best among all four. So this is good on our part. And yeah, so that was it. And this, for a conclusion, I would say like we propose the model WTM, which does topic modeling and visualization for short text, and it leverages the information from word embeddings to do that. And we conduct like an extensive set of experiments to like compare the performance of WTM. And then it was good that we came out on top. So thank you so much, and have a good day.